November 7, 1940. Washington State. A bridge unlike any other trembles violently in the wind, twisting and flapping as if alive. This is the infamous Tacoma Narrows Bridge, nicknamed Galloping Gertie. Today, we'll explore why this bridge was built, how it was constructed, the engineering mistakes that led to its collapse, and what happened afterwards. Its story is one of innovation, disaster, and lessons that changed engineering forever. The Tacoma Narrows Bridge was designed to connect Tacoma and the Kitsap Peninsula across the Puget Sound. Before the bridge, traveling between these areas meant long ferry rides that could be delayed by weather or mechanical issues. Local leaders wanted a bridge that would improve transportation, reduce travel time, and stimulate economic growth in the region. The vision was for a long, elegant bridge that would be a marvel of modern engineering, drawing attention nationwide. The bridge was designed by Leon Moisseiff, a respected engineer known for his work on suspension bridges, including the Manhattan Bridge in New York. Moisseiff pioneered ideas that allowed for longer, lighter bridge spans. The Tacoma Narrows would be the third longest suspension bridge in the world at the time, with a total length of over 5,000 feet and a main span of 2,800 feet. The design was striking, with a narrow, graceful deck suspended high above the water, giving the impression it almost floated in the air. Construction began in 1938. Workers erected massive steel towers and suspended the narrow roadway using thousands of steel cables. The deck itself was light and made from shallow girders, which made it economical and quick to build. But this same lightness would later prove dangerous. The project cost roughly $6.4 million, equivalent to over $120 million today, and employed hundreds of workers who risked their lives high above the water each day. The bridge was a technical marvel, but it was also pushing the limits of contemporary engineering. The bridge's flaws were hidden in its elegance. The narrow, plate girder design lacked the stiffness of traditional deep trusses. Without rigid support, the bridge could move easily with the wind. Engineers at the time underestimated the effects of aerodynamics on long, lightweight bridges. They did not anticipate that certain wind conditions could create resonance, a feedback loop where the wind would match the bridge's natural frequency, amplifying its motion with every gust. This would later prove catastrophic. Shortly after opening in July 1940, the bridge began to behave strangely. Drivers reported the road rising and falling like a wave. Pedestrians holding onto the rails could feel the bridge sway side to side by over 8 feet. Engineers were alarmed but did not fully understand the danger. The public dubbed it Galloping Gertie, and newsreels captured its dramatic movement. Some drivers refused to cross, and local newspapers were filled with stories of the bridge's peculiar dance. The fatal flaw was torsional oscillation. Unlike simple up and down bouncing, the bridge twisted along its length. On November 7, 1940, a steady wind of about 40 miles per hour caused this twisting motion to amplify until the bridge could no longer withstand the forces. Sections of the roadway tore apart, collapsing into the Puget Sound below. Engineers later realized that the combination of a narrow deck, shallow girders, and flexible design created the perfect storm for aerodynamic failure. The collapse was captured on film and became one of the most famous engineering failures in history. Amazingly, no human lives were lost, though a dog inside a car perished. The bridge's destruction sent shockwaves through the engineering community. It became a case study for decades to come, demonstrating that elegance and economy could not replace safety and structural integrity. Engineers analyzed every piece of wreckage, searching for answers. The disaster led to significant changes in bridge design worldwide. Engineers learned the importance of wind effects and aerodynamics. Wind tunnel testing became standard, and torsional stability was prioritized in all future long-span suspension bridges. The Tacoma Narrows Bridge is still studied today in engineering schools, reminding students that innovation must be balanced with safety. In 1950, a new Tacoma Narrows Bridge opened, built wider, stiffer, and safer with deep girders and a reinforced deck. A second bridge opened in 2007, further modernizing the crossing. Today, thousands of vehicles cross these bridges daily without incident. Interestingly, engineers still study footage of the original Galloping Gertie to understand resonance and oscillation in bridge design. The story serves as a powerful lesson that even remarkable engineering can fail if natural forces are underestimated. The Tacoma Narrows Bridge disaster wasn't just a dramatic collapse. It was a story of human ambition, error, and resilience. From a wobbly bridge that danced in the wind to the stable structures we see today, it shows how failure can lead to progress. If you enjoyed this deep dive into one of history's most fascinating engineering lessons, make sure to like, subscribe, and hit the notification bell. And remember, next time you cross a bridge, it's probably standing thanks to lessons learned from Galloping Gertie.